Welcome to Unstuck. Today a single function inside the DeFi router let a stranger spend other people's tokens and drained about $13 million. We will look at the one line that did it, prove the drain live in Remix step by step, read and run the Foundry test and watch it fail on a real block explorer, then fix it in one line. No prior knowledge needed. This is the heart of it, a router with a function called execute. You hand it a target address and some data and it makes that call for you. The highlighted line does it, target.call with your data. Convenient for an aggregator, but it will make absolutely any call you ask for, and that is the whole bug. First, what a router is, it is a helper contract that swaps and routes trades for you. To let it work, you approve it, giving it permission to move your tokens. This is completely normal. Every exchange asks for an approval, but it means the token already trusts the router to move funds on your behalf. Hold that thought, because trust is exactly what gets abused. Now the exploit is a chain of calls. Step 1. The attacker calls the router's execute, choosing the target and the data. Step 2. That data is a transfer from taking the victim's whole balance to the attacker. Step 3. The router runs it, and here is the trick. The call happens with the router as the sender. Step 4. The token sees its trusted router asking and thus moves the victim's tokens. The attacker never owned them, they just asked the trusted middleman to move them. Back to the code, the vulnerable line highlighted in blue, target.call data. There is no check on what target is or what the data does. So the attacker sets target to the token and data to a transfer from that drains anyone who ever approved this router. $30 million left through exactly this line. And here is the fix. The same router with one highlighted line added to execute. Require allowed of target. Why target? Because target is the address the router is about to call, the thing that could be a token holding someone's approval. Why an allow list? Because the owner decides upfront the small set of contracts this router may ever touch. Anything else, including an attacker's chosen token, is refused before a single token can move. Let's prove it live in Remix, a browser solidity playground. Our contract is already compounded. On the left we deploy and call functions. On the right is the code. Nothing is hidden, so let's run the real attack. First, we deploy the vulnerable version. Its constructor quietly builds three things: a token, the vulnerable router, and an honest victim, a user who has already approved that router to spend their tokens, exactly like you approve a real exchange. One click and it is live on the right. Let's check the victim. We call victim balance. This function simply reads the token's balance for the victim's address and returns it. It shows 1 million. So the victim is holding 1 million tokens, sitting there safely for now. Now the attack itself. Watch the chain of calls. The attack function builds a payload. The tokens transfer from, moving the victim's whole balance to us. It hands that payload to the router's execute. The router makes the call as itself. The token sees its trusted router and it obeys. So one single click triggers that entire chain. Did it work? We call victim balance again and it is now 0. The victim is completely empty. Then we call attacker balance and it reads 1 million. Every token the victim held is now ours. We never owned them, we just asked the trusted router to move them. That is an arbitrary call. Now we deploy the fixed version. Same token, same honest victim who approved the router, but this router checks an allow list before it makes any call. Everything else is identical, so it is a fair test. We now run the very same attack. This time execute first asks a question: is this target on the allow list? The token was never added, so it stops immediately. Revert, target not allowed, and when we check the victim, still 1 million untouched. The very same attack completely blocked by that single line. Remix showed it by hand, now a repeatable automated proof. This is the Foundry test for the vulnerable path, highlighted. It deploys the demo, checks the victim starts with 1 million, calls attack, then asserts two things. The victim ends at 0 and the attacker ends with 1 million. If those assertions hold, the drain is real. Let's run it. There it is, victim before 1 million, it runs the attack, victim after 0, attacker after 1 million. The test passes, and passing here means the assertions held, the victim was drained and the attacker took everything. Proof number 2. And the test for the fixed path highlighted. It runs the identical attack but wraps it in expect revert, target not allowed, and then asserts the victim's balance never moved. In plain terms, it proves the attack is blocked and nothing is lost. Let's run it too. It passes, the attack reverted exactly as expected, and the victim's balance stayed at 1 million. So the fix does not just look right, it provably blocks the exact attack that drained the original contract. And this is not just a local sandbox, we deployed the very same contract to the Sepolia network and verified it on Etherscan. Source code verified, exact match. Anyone can open this address and read the vulnerable execute function for themselves. Here is the attack as a real transaction. Etherscan decodes it as a call to attack and it succeeds. The arbitrary call runs on a live chain and moves the victim's balance. The drain recorded permanently in a block you can click through yourself. And the same attack against the fixed contract on the same network. Status fail with the error target not allowed. The allow list stopped it on chain, exactly as our test predicted. A real decoded failed transaction. The fix proven in public. Side by side, the old router forwards any call, so it happily spends the approvals it was trusted with. The fixed router checks the allow list first, so an arbitrary call to a token simply cannot happen. The rule underneath, never let untrusted input choose both the targets and the call date of a call your contract makes. The takeaways: any call your contract makes inherits your contract's trust, its approvals, its rules. So an arbitrary call is arbitrary power. If you must forward calls, whitelist the targets and never forward user-controlled target and data that could move funds. And every time you see a low-level call, stop and ask, when this runs, who is the sender and what have people trusted that sender to do? Recap: the routers execute made arbitrary calls as the router. Users had approved that router, so it could already move their tokens. The attacker just asked it to, pointing it at the token. With a transfer from that drained the victim. The fix is a single allow list check before the call. We saw it in Remix, in the Foundry tests, and live on Etherscan, the drain, and the one line that stops it. A quick note: if these breakdowns help you ship safer contracts, the wallet is on screen and there is a Ko-fi link in the description. Every tip funds the next reconstruction. Thank you. Your turn. Comment the heck you want me to reconstruct next, and I will build it live just like this one. If it helped, hit like and subscribe so you catch the next one. This was a genericized reconstruction, the lesson, not the names. Thanks for watching, and I will see you in the next one.